Let us look at the second type of the stereoisomerism, which is called geometrical isomerism. Now, in geometrical isomerism means that there are two or more compounds with same molecular formula but different arrangement of atoms in space. In space, they have been arranged in a different way. Their formula is the same, their name is the same, but they have different arrangement around themselves in space. Now look at this, at what two typical conditions which are required for this type of isomerism is that the compound must have a C-C double bond. That means that alkenes can show this type of isomerism where C and C double bond is present. The second requirement is that the two groups on each carbon atom, there are two carbon atoms present here, on each carbon atom there should be two different groups. Like on this CC, I can see R1, R2, R1, R2. Both R1, R1 are on both the sides, but this single carbon atom has two different groups. Now, why does this geometrical isomerism take place is that in a double bond compound, you already know that in a double bond compound, there is a sigma bond and there is a pi bond. A pi bond means that there is a p orbital which is overlapping sideways. So there is a p orbital like this, which is above the plane and below the plane. There are two p orbitals above the plane and below the plane, and they are overlapping from top and from below. Now what happens is that in a single bond compound, if supposing I have a single bond compound which has groups like this. In a single bond compound, I can write these groups anywhere I like. I can change this compound if I want to write it again. Another child might write C2H5 here, H here, OH here and CH3 here. The name of the compound will not change because in a single bond compound, complete rotation is possible. So in a single bond compound, there is complete rotation, and due to this complete rotation, the compound does not change at all. But in a double bond compound, there is rotation only till certain extent. Like this is the p orbital, it can move only till here. If it starts moving completely, it breaks. So there is a p orbital overlap on this point, which is going to move halfway. And this halfway movement of p orbital is known as restricted rotation. That is, rotation is not complete, but it is restricted to some point. So it is moving, but moving till here, cannot move till here. So this compound, which contains, say, there are two carbon atoms here, there is a double bond here, and there is CH3, CH3, Cl and Cl. Fine. I can write this compound this way, that CH3 and Cl written here. On this side, I have changed CH3, moved here, Cl here. So restrictedly, I have moved only halfway. This can be done. And now the compound's name is same. 2,3-dichlorobutene. At place 2 and 3 are two chlorine groups. And there is a double bond at place 2. So 2,3-dichlorobutene. Same is the name for this compound. Now, what difference does it make is that here two chlorine atoms are on the same side, so the pull is on the same side, whereas here chlorine atoms are at opposite ends, so pull is on the opposite ends. So the pull is getting, since it is from both the ends, it is getting cancelled. So when it is getting cancelled, we will say dipole moment here is less, whereas here dipole moment is more. So this compound where two chlorines are on the same side is known as the cis isomer. Where they are on the opposite sides is called the trans isomer. So cis and trans are two isomers of geometrical isomerism, in which trans means across, like trans Gomti you say, so across the river. So this is across. So trans isomer and cis isomers will be seen in any double bond compound. The same compound I could have written as, supposing, instead of here there is H, there is H, this is H, and this is H. Again, H and H on opposite ends, CH3 and CH3 on opposite end becomes trans, and both of them are but2ene. All four groups in a double bond compound can also be different. Those will also show geometrical isomerism. But if in a question you are asked whether this compound will show geometrical isomerism or not, you will first check for a double bond, then check whether each carbon atom has same groups or different groups. Supposing I write it this way. There are same groups on this carbon atom, but different groups on this carbon atom. You will say this compound will not show geometrical isomerism. Both the carbon atoms should be such that they have different groups.